following on from last time, time we talked about fusion. Sorry, Tom.
Action.
Last time we talked about fission, like big nuclei getting impacted by a neutron and starting to globulate around and then splitting in half. The kind of opposite process, in a sense, is fusion, which is when we have two small nuclei, we collide them together and it forms a bigger nucleus. This is a little bit of a simplified process. It's not quite as simple as 2,1H plus 2,1H makes 4,2He, but that's kind of if we distill down to like really what's going on, that's kind of what's going on. We're banging together hydrogens often, or small nuclei, to make a bigger nucleus. What are the difficulties that we have to overcome with fusion?
Charge.
Yeah, what's the difficulty?
Needs very hot.
Needs lots of energy.
Strength, force to mash them together.
Energy, strength, force, mash. Yeah. So these 2,1H's, these are hydrogen nuclei, and so they've got a positive charge. So each of these have got a positive charge, and yet we're bringing them together close enough that the nuclear strong force can take over and bind them together into one nucleus. How close do they have to get?
One nucleon.
They have to be touching. Effectively, they have to be touching our nearest neighbour nucleon. They have to be within one nucleon of each other. So we have to get these things really close together, but they really don't want to be close together because they've each got a positive charge. And so the way that we get them to be close enough together is they have to be going really, really fast. And because we're talking about particles, we know that fast talks about temperature. Right? Like temperature is the average kinetic energy of particles. If we want our particles going really fast, we need them to be really, really hot, really high kinetic energy, so that they're moving fast enough that they can collide and stick together. What's the other thing that we need to have in order for fusion to take place?
Like particles.
We need particles, yeah, we need stuff to bang together, but they need to be going fast. And on the sun, what's the sun like?
Warm.
It's hot pressure, yeah. It's got lots of gravity, it's really massive, lots of gravity, really high pressure. That means that not only are these things moving really fast, normally, if we heat up a gas, it expands, right? Which means that the particles are further apart, so there's less likelihood of colliding. We need them to be moving really fast, but also at really high pressure, so that if they do collide, it's going to be a successful collision. The high pressure is going to make it more likely for them to collide.
Oh, rates of reaction. Some chemistry stuff right here.
Hey, this is another one of those bits of chemistry curriculum that they ran out of chemistry, so they borrowed some physics.
Why didn't we even do chemistry last year?
What?
We could have done physics.
This year,
Except for surely it's called free.
Like what?
Not like
But I actually
Okay. Titrations are irrelevant.
ions in a solution.
No, you're wrong.
Titration was so good. It was like easy credits. Yeah.
Oh, yeah.
Titration's just fun.
Go.
Okay, so fusion is what happens on the sun. The sun is a good environment for fusion. It's really hot, so the particles are moving fast, and there's lots of gravity, so there's really high pressure, so they're likely to collide. We don't worry about the electrons when we're thinking about fusion. The electrons have been stripped away, so we've just got a plasma of like nuclei that are zooming around, buzzing around, hopefully crashing into each other. We would love to make fusion happen on Earth because it's clean and we're burning water to make helium. We're burning things that are not radioactive to make something that's not radioactive, releasing lots of energy. It's in the oceans already, like we've got this stuff. We would love to be able to do fusion on Earth, but it's difficult because we don't have containers to do it in. It's really hard for us to work out what containers we can do it in. Something that can withstand high pressures and high temperatures at the same time. Ways that people are trying to do this, the two main ways that they're trying to do it are with a donut-shaped magnetic field, and so they're constraining the high energy particles to be within this donut-shaped magnetic field, and so they're travelling around in circles within this donut-shaped magnetic field, and so there's no actual physical material that's constraining them, it's the magnetic field that's constraining the particles. That's one way. The other way is by firing lasers at samples that contain hydrogen, and the laser is providing both energy to get the high temperature and also pressure to keep the materials at high pressure. Those are kind of our two ways. Someone was talking the other day about, like in France, they're having a go at cracking one of these things.
These magnets.
Magnet, so that's the donut-shaped magnetic field.
Wait, how long
Ice cream.
would you need to keep
High
those
pressure?
conditions in order to get like enough energy for it to be worth it?
So we can, we can quite easily, we can make the conditions, like we can fire a beam of, we can accelerate a beam of protons, like heavy protons, at a sample that's got more heavy protons and have them going fast enough to make it happen. But it's containing that and making it self-sustaining that's difficult. Like we can put energy, we can put a lot of energy in and make this reaction happen. We can do that, but then how do we kind of make it self-sustaining? How do we make it like extract energy from it and use that to keep it going?
So it
That's
would
the
have to be
trick.
like continuous in order to get the energy from it.
So what we're trying to do is make it continuous. The energy is just heat. Like these things are going really fast. So we're just collecting heat from it. All of these like nuclear energy sources are just like the same sort of technology as a coal-fired power plant. Instead of burning coal, you're just using nuclear fuel to make heat.
Heat the water.
To heat the water, to turn the turbine turns the generator, makes electricity, charge yourself.
Nothing.
Yeah.